Okay, we're now going to work on doing a more annoying example of the Euclidean algorithm. Let's try to pick some numbers. I have some numbers that don't work out quite as nice here. They don't have to be big not to work out well. It's just going to be a longer problem. So let's try to find a GCD of 28 and 71. Okay, so I know that 71 is going to be 28 times 2. Can't get 3 28s into 71, that would be too big. So 28 times 2 is 56, so that would leave 1, 2, 3, 4, 5, 15 plus 15. Okay, so then I put 28 there, and let's see, how many times does 15 go into 28? Well, only 1. Okay, well, I move the 15 down. How many times does 13 go into 15? Well, only 1. And then how many times does 2 go into 13? Well, that's going to be 6 plus 1. And then how many times does 1 go into 2? Well, that's 2 plus 0. So that's the GCD. 1. Okay, so what does this tell us? It tells us that the two numbers have no divisors bigger than 1 in common, and because of this we can use Dylqu's algorithm to express any number at all as a linear combination of 28 and 71. So let's try to use Dylqu's algorithm here. Now, I want to express 1 as a combination of 28 and 71 first. So I know that 1, let's use this line right here. 1 is going to be equal to 13 minus 2 times 6. Okay, so now I use this line for the 2. So I get that 1 is equal to 13 minus, okay, and the 2 is 15 minus 13. So I get, so let's see, I have 13 plus 6 13s, that's going to be 7 13s, minus 6 15s. Okay, so now I have this line, and I'm going to use that to plug in 13, because I have a nice 13 right here. So I get 1 is equal to 7 times, okay, so for 13 I get 28, minus 15. So, and this is still the minus 6 times 15. Okay, so I get 7 times 28, and then it's going to be minus 7 15s minus 6 15s, so minus a total of 13 15s. Okay, well, we're getting a little closer. I said this was going to be more of an annoying problem. We've got a lot of steps before we can get all the way back. So I can now plug in that 15. 1 is equal to 7 times 28, and then this is minus 13, and then I get 71 minus 28 times 2. So this gives me 1 is equal to 7 times 28 minus 13 times 71, and then this is plus 26 times 28. So this gives us 1 is going to be, well, 26 28ths and 7 28ths gives me a total of 33 28ths minus 13 71s. So we've now expressed 1 as a combination of 28 and 71. So 33 28s and 13 71s that gives us 1. So any other number that we want, we can now express as a combination of 28 and 71. For example, I don't know, 3. This would be 99 28, and then minus 13, 26, 39 71s, still with the 28 and the 71. So we can express any number as an integral combination of 28 and 71. This is useful for a number of word problems or real-life problems, because sometimes you need integer solutions because fractional or decimal solutions don't make any sense. It's a useful technique. It's not that hard, even in this case, though it can be a little tedious if the numbers don't work out so nice, as we've seen here.